We move on to capacitors. Any two parallel conductors can be defined as a capacitor. As you can see here, if you connect one of the conductors to the negative electrode of the battery and the other plate to the positive electrode, so now the same potential difference between these two electrodes is equal to the potential difference between the plates. This is positive electrode, so you have positive charge here. This is negative electrode, so you have negative charge here. Each plate has an area A, and they are separated by a distance D. Such a structure is called parallel plate capacitor. We can use it for two main goals: to store electric energy or to produce an electric field. So here, between the positive charge and the negative charge, there will be field lines that we can use for all kinds of applications, like to control the motion of electric charges. The ratio between the charge Q and the resulting voltage difference V, this ratio is called capacitance. So capacitors have a property which we call capacitance, that we can measure from the ratio between the charge and the voltage difference. The unit for capacitance in the SI system is a unit of charge per unit of voltage, so it's coulomb per volt. This unit is called farad, honoring Michael Faraday for his contributions to the field. Farad is a big quantity. Because of that, when we deal with capacitors, the unit that is most common is the microfarad, which is 10 to the minus 6 farad, or the picofarad, which is 10 to the minus 12. From this defining formula, we can solve for Q. Q equals C multiplied by delta V. So if you have a capacitor with capacitance 3 microfarad connected to a car battery 12 volt, this means the charge in the capacitor can be calculated from this equation. It is equal to 36 microcoulomb. The two plates carry equal amount of charge, except one is positive, the other is negative. The electric field between them can be calculated as we did last chapter using Gauss law. Between the two plates, the field is sigma divided by epsilon naught. Sigma is the charge density, Q divided by A, that is the surface charge density. So the electric field between the two plates is sigma divided by epsilon naught. And we can solve for the voltage difference. It is E multiplied by D. This is how we calculate the voltage difference. So once you know E and you know D, you can calculate the voltage difference. Q can be calculated. Q equals sigma A. So now back to the defining formula for capacitance. Q divided by delta V. Q sigma A and delta V is ED. So we end up with this result. Substitute for E, it is sigma divided by epsilon naught. So now sigma cancels with sigma, and we end up with this very important equation for the capacitance: epsilon naught A over D. So now we know how to measure the capacitance for any parallel plate capacitor. Simply take the area and divide it by the distance and multiply by epsilon naught, 8.85 by 10 to the minus 12, the permittivity of free space. This is when this medium is vacuum or air, the same thing, same permittivity. This is how we calculate the capacitance. An alternative way to calculate the capacitance is to measure the charge and measure the voltage. Then from the ratio between the charge and the voltage, you get C. Either way is fine. And as we proved here, the two approaches are identical for measuring the capacitance of a capacitor. The electric field is homogeneous inside the capacitor. But if you move near the edges, we have the so-called this fringe effect or edge effect. So now the field is not really homogeneous. In most applications, we use the central region of the capacitor so that we have a homogeneous field. We don't care much about the edges. One application that we all use is the keyboard. Have you ever wondered what's happening when you press one of the keys on a keyboard? So now you know what's there. You have a parallel plate capacitor. When you press the key, the separation between the two plates is reduced, is changed. Reducing D, when you reduce D, the capacitance increases. Okay? So eventually, when you press any key, you are reducing the distance and increasing the capacitance. Usually there is an insulating material called dielectric between the plates here. And from the change in the capacitance, the processor, the brain of the computer, will take note that the letter B is pressed, for example. Okay, this is how we key in information to computers. When we build electric circuits, it is easier to deal with symbols. Usually we use this symbol for capacitor regardless of its shape. We use this symbol for batteries. This is the positive electrode and the short dash is the negative electrode. We use this symbol for resistance. This symbol for light bulb. So for example, rather than drawing this circuit this way, it is more convenient to deal with symbols and draw it this way. So this battery is replaced by its symbol, the light bulb replaced by its symbol, and the resistor is also replaced by its symbol.